Okay, so at long last, we're ready to start chapter 8. Okay, now I did mention that chapter 8 is where we'll be learning about a lot of far more complicated integration techniques. You already have some background in that area, but they're going to show us some new techniques that will give us a lot more cases that we can handle. But we have to make sure that we still understand the basic rules. So they're going to start us out by reviewing the basic integration rules. Then we're going to practice with them a little bit, and then we're going to start to learn the new techniques that make it possible to integrate a much larger variety of functions. Okay, so let's begin with the basic rules one more time. Now, um, they've got a list in here, which of course you can find in the back of the book. In fact, in the beginning of the semester, I mentioned that I did post a list of or the rules of integration, but in this chapter, we're going to start with these. And if you notice, everything is written in terms of u rather than just x. So it's understood here that u is a function of x, which means that in some cases we need the chain rule to get our results. Okay, so we'll keep that in the back of our minds. And you can see there's 3 pages, of which the last two are trig integrals, or in the last few, these are arc sine, arc tan, and arc secant. And the art here in doing integrals really is to understand or recognize which one of these we're dealing with. And if it's not one of these, we want to know if we can rearrange the integral algebraically into a form that can be handled by one of these basic functions. Okay, so it is definitely an art form, recognizing when you look at an integral, is it one of these basic rules? If not, is there something I can do to rearrange it and simplify it somehow so that I can, in fact, use these rules after all? So we're going to get a lot of practice with these ideas. So here, right off the bat, we have some cases. We have 3 integrals they'd like us to solve. So let's begin with the beginning. All right. Now, the first thing you want to look at is, well, are there any basic rules that might apply here? So let's come back to the basic rules and see if any of them look familiar. So what do we have here? We've got in the denominator x squared plus 9. And you could think of both of these as squares, by the way, because of course 9 is just 3 squared. So in fact, it looks like this might be the one we want right here, because if we replace um, x, the u becomes x, and the a becomes 3. Well, then what do we have here? Well, now, of course, the 4 in the numerator, we can just factor it right out. We don't care about that. Oh, and of course, I almost forgot. If u is x, then du is just dx. So it looks like we're all set here. Because if I make these substitutions, look what I have. Yep, that's it. U squared plus a squared. Okay. And that tells me that it's 4. Keep the 4 on the outside. 1 over a, which is 1/3. Arctan. U over a is x over 3. And then, of course, we have the constant of integration. And that's our answer. We're done. Okay. Of course, you can distribute the 4 if you want, but this is our answer. All right. And just a quick reminder, arctan, if you remember from a previous class, um, sometimes arctan of, let's say, now the arctan could be any number. Um, let's say, I'm not sure if I should make up an example on the spot, but what it's trying to get at here is that, let's say we're looking for the arctan of x. Um, what you're really solving for is there's got to be some angle whose tangent equals this number. That's what we're really looking for. But I also want to remind you that this is sometimes written as tan with a -1 symbol. As a matter of fact, if you wanted to look this up in your calculator, um, it's there. You have to know where to look. If you have, for example, the TI-84, um, let's see, maybe I'll just make up a quick number here. All right, that's, well, all right. It says here that the arctan of, I just realized I'm in the wrong mode. Hold on one second. No, that's a lot more like it. Okay, so I was able to make up a good quick example, but I was in the wrong mode. I was in the radians mode. I wanted degrees, so now we're all set. So arctan of 1 is 45 degrees. Simply reminds us that the tangent of 45 is 1. Okay, so the arctangent is simply the inverse of the tangent. Okay. So, the book, it looks like the book is going to write it as arctan, but just be aware that it's the same thing as tan to the -1 power that you're seeing on your calculator. So if you need to calculate it, it's right here. In fact, how did I get this number? I put second tan. Of course, if you notice directly above it, it says in tiny little letters, tan -1, and then you type the 1 and then enter. And as long as you're in the degrees mode, it'll come back with 45. All right. Anyways, so this is how we do. In a case like this, it was a question of recognizing this pattern by looking at the chart of basic integration rules and recognizing that it was this one. Okay. Now, sometimes we'll get lucky and we'll find it right there. Sometimes we won't, but it might turn out, like I said, that you can rearrange it algebraically and suddenly you have what you're looking for. They're going to show us a list later on of the techniques you could try in case you can't find what you're looking for in these slides right here. All right, now how about this one? That one looks a little bit messier. It doesn't look like this one is going to be something we can read right off the list of basic rules. We're going to have to try something a little bit more advanced. And well, first, of course, we can factor out the 4. We don't have to worry about that. So here's an idea. How about if we try U substitution? Well, if that's the case, let's try u equals x squared plus 9, which means that du dx is 2x, which is the same thing as saying that du is 2x dx. All right, so let's write this down again. Now, there's just one problem, of course. We don't actually have here 2x dx, we have x, but that's because the 4 is on the outside. So here's what I have to do. Without changing anything, I'm going to rewrite this. Okay, you can see algebraically I haven't changed anything, but all of a sudden, look what I have. Uh, and now you probably recognize this one as the natural log of u plus c. Now, if you notice, we can drop the absolute value signs because this expression can't be negative. All right. So in this case, looking directly at the rules was not the way to go. All right, it just wouldn't, we never would have found it. So instead, we try something else that we know how to do, which in this case turned out to be U substitution. Now look at this one. What do we do now? Well, U substitution is not going to work. We won't have the right dx, or du rather. What can we do? Now, here's where you might want to start thinking about doing some algebra. Um, so the book is going to recommend that we do this. Now, this is something you might not think about, but you could actually use long division to split the ratio into two simpler terms. All right. So what does that involve? All right. Well, oh, actually, looks like they mean for us to leave the four on the inside here. I'm not sure if it really matters, but let's just put the four back. So here's what's going to happen. You probably remember doing this in your travels. So it's essentially long division with polynomials instead of numbers. So you could put a four here, for example, which indicates that if I multiply 4 by x squared plus 9, I get 4x squared plus 36. And then I can subtract. Both of these become negatives. This drops out. And there's no x's, so we're just left with 36. So in other words, what this is saying is that, okay, so now if we try to integrate this one, I think you'll agree that it's a little bit easier because the first one is easy because we can just use the power rule. The second one is one of our rules. In fact, it's the arctangent again from before. All right, let's go grab that one back. That's right. We see our friend the arctangent here. And so what do we have here? So just like before, u is x squared plus sorry, it's just x squared. A is therefore, oh, I'm sorry. No, no. U is x because it's x squared. Sorry, it's just x because we have it's got to be squared down here. And that implies that A is 3. So we got minus 36. And based on our formula here, we'll have 1 over A arctan x u over A, which is x over 3, plus c. Okay. So it's 4x minus, now if you multiply this out, and you're done. Okay. So what was the big, well, now this one, this was a tricky one. Who would think to do something like that? But sometimes that's the way to go. If you can break it up into two simpler pieces, then you're all set. Or at least we were in this case. So, like I said, it is kind of an art form, trying to recognize the different ways we can manipulate the integrals to into something that matches one of these rules. And it's not always going to be obvious. Um, anyway, so here's another one. So again, the first thing we need to do is look at our rules, our basic rules. And you can see, let's go take a look at them. We need a square root with some constant squared minus u squared. Ooh, this one looks promising. Hold on, let's try this one. So imagine that we let a be 4 and u is actually x cubed because when we square it, it becomes x to the sixth. And then our du. All right, so we don't have 3x squared, but we have x squared. So we can rewrite this as so. And I think we're in pretty good shape now. And according to what we're seeing here, and we're done. Wow. All right. So there's a there's another one we know how to do. So you might want to print out these and keep them handy when you're doing the um, WebAssign problems because you'll probably need them. All right. Now, here, this one, they're kind of playing games with us a little bit. They're telling us try these and see if they fit with any of the rules, the basic rules that we have up here. So I checked it out. I can tell you in advance, the third one does not. Okay. It requires a string of very messy trig substitutions. So that means the answer is no to that one. But we can do the first two. Okay. So let's try them. Now you can start to see these are starting to look familiar after you've done enough of these. All right. So you can easily imagine here, for example, that if A is set equal to 1 and U is X, then we have. Oh, of course, that implies that du equals dx. And I think we just had this one, right? Yes, we did. What do you know? All right, so then what do we have? Three arc sine u over a, or very simply, three arc sine x plus c. Now, I think, if I'm remembering correctly, they did not bother to give us the answers here, but we can confirm this by just differentiating the answer and making sure it turns back into this. Okay. All right. So that's that one. I did say, now the next one is also reasonably straightforward, but at least it works. Okay. So let's try this one. It kind of looks like another one we've already seen with U substitution, doesn't it? Yeah, it does. So look, watch this. And if we use that approach, we do have to make a change because we have a 3 here instead of a 2. And by the way, then we can assume that um, no, we don't have an A here. We don't need it. It's not going to be one of those formulas. So we need 2x up here. Okay, that should do it. Oh, I just realized I goofed. This u shouldn't be x squared. It should be the whole expression, 1 minus x squared. That's better. Then du dx is actually negative 2x dx. So we need negatives here and here. All right, so now we're getting there. Okay, so we got negative 3 halves du over the square root of u. All right, now we're good. Okay. So 1 over radical u is, and of course, based on the power rule for integrals, we have we can write this as minus 3 halves. So now we're going to add 1 to negative 1 half. So we're going to end up with 1 u to the 1 half over 1 half. Now, of course, dividing by 1 half is the same thing as multiplying by 2. So we end up with minus 3 radical u plus c. And of course, u itself is, as we set up here, 1 minus x squared plus c. All right. Okay, and like I said, we're not going to do, they're only interested in knowing if this can be done in terms of the basic rules that we just had, but no, no, no. If you could see what needs to be done, you'd agree right away that this is not one of those cases. Anyway, let's try. Now here, they want you to remember the Pythagorean identities because you might need them. So you might remember the one nobody ever forgets is this one. This is taken directly from the Pythagorean theorem, but the next two are basically implied by the first one. They're not really separate conditions. And then the third one involves a cotangent. So in other words, if you wanted to prove, let's say you wanted to prove this one, let's say you feel so inclined. You're like, I feel like I want to prove this. I don't want to just write it down. So you would start here, and then all you would have to do is divide all these terms by the cosine of x, which you're certainly allowed, cosine squared of x, which you're certainly allowed to do. Now, Of course, you remember that the sine over the cosine is the tangent, which means that if you're taking the ratio of the squares, it will just give you the squared tangent. The middle second term is just one, and also if you remember, the cosine is one over the secant. So therefore, you've got, and that's where the second one came from. Tangent squared x. Oh, what did I do? I wrote the wrong one. Sorry. Tangent squared of x plus one equals the secant squared of x. Okay. And then the third one, you'd go to the first condition and divide across, not by the cosine, but by the sine, and you'd end up with a correct result. Okay, so that's where they're coming from. All right. So in other words, they're correct. All right. So anyway, they want you to remember this because if you have something like this, tangent squared of 2x dx, sorry, 2x, they'll point out to you that this is not one of the basic results, is it? In fact, let's go back to the list. And in none of the cases will you see an integral for the tangent squared. There's a lot of trig functions here, but that's not one of them. Okay, but there is one that involves the secant squared. So that means that's a clue. So what they're saying is, well, um, based on what we just saw a minute ago, and therefore, oh, sorry. No, that's not what I meant to do. The tangent squared could be rewritten as something much more convenient. And that's going to get plugged in up here. So in other words, we can replace this with, oh, now we're getting somewhere. Look at that. Now, of course, you notice how there's a u here. That u it would have to be 2x. That means du is 2 dx. We don't have to. We have to supply it. So here's what we'll do. And you can see I haven't changed anything. But guess what? All of a sudden we have secant squared u du, which is what we need. And so according to the rule, that should give us the tangent of u. But don't forget the 1/2. And then the integral of dx is just 1. Sorry, x. It's just x. All right. And there we are. So that was a little tricky. Man, there's so many possibilities here. All right. God, what else? Okay, now here's where they're starting to give us some helpful hints. These are all helpful ways in which you might be able to take a very messy expression and turn it into something more manageable, at least as far as the integration is concerned. So we have expand the numerator, just multiply it out, break it up into two simpler pieces, complete the square so that you can use one of the trig integrals and divide, which we just did a few minutes ago. An improper rational function means that the degree of the numerator is equal to or greater than the denominator. Okay, that's what it means to be improper. And so when that happens, we can use the technique we just saw, long division, and break it down into something much more manageable so that the terms, individual terms, might have a rule that we can use, whereas the original expression did not. So there's a lot of possibilities here. And you can see there's so much to think about. So, anyway, oh, now here's another case. Now, here's a really, who would think to do something like this? You notice they're using the word Pythagorean conjugate. The word conjugate generally means you've got something like this going on. You might remember from your travels that if you had two complex numbers, which are only different by the sign, they're referred to as complex conjugates. So this kind of thing, 1 plus sine x and 1 minus sine x, could be considered a type of trigonometric conjugates, or they're calling them Pythagorean conjugates. Okay. So sometimes we can use that to simplify what we're doing to something more manageable. So here's the example they decided to give us. 1 over 1 plus sine x, which we don't have any rules for that. But if you notice, the Pythagorean conjugate of 1 plus sine x is 1 minus sine x. So we multiply the expression by that over itself, and we ended up down here. And well, they didn't take it any further, but we should be able to do something with these. Okay. All right. So we're going to take a shot at this one. It isn't actually too bad. Okay. Um, so let's see what we can do here. So the first thing we of course think about is breaking it up into pieces. By itself, I mean this thing, there's no rules for this. So actually this one looks pretty promising because you're basically just going to apply the power rule in both cases. So when you add 1 to -4, of course, it becomes -3. And, unless you want to simplify it, that's the answer. So let's see what they did. Yeah, okay. Um, looks like they rewrote it as, and that makes it letter C. Okay. Okay. All right. So, this again, this is one of those topics where, the only way to really get any good at this is to just keep practicing. And I'm sure that in WebAssign, they're going to give you a lot of these to deal with, and they'll all be somewhat different. So, but the idea here is ultimately you want to break up whatever you're dealing with to something simpler using one of the techniques they showed you so that you can follow it or solve it with one of these basic rules, they're calling them. Anything beyond that, we, of course, is what's coming up next in the chapter. So, for example, in 8.2, we're going to see another technique which is going to enable us to solve integrals of a specific type. And now this is referred to as integration by parts. And so this one is really good for when you have an integral of a product of two fairly complicated functions. For example, now look at these. Now, if you saw these without what we're about to learn, x, ln x, what do we do with that? X squared e to the x. Oh my God. E to the x sine x. These are all um, very good examples of tech, integrals that we can solve for with this method of integration by parts. Okay. So as soon as you see a product like that, think about integration by parts. So here's how they're going to derive it for us. You got to be a little careful with the notation here, by the way. This is the starting point. So this is section 8.2. Okay. Um, so you notice how sometimes they use f prime of x, they use u, they use dy dx. There's a lot of notation that means the same thing, but there's certain notations that tend to be used for certain applications, and this is one of them. Um, so the derivative of the product of u and v. Now they're assuming here u is a function of x, and so is v. All right, so be aware of that. So that means what you're doing here is you're using the product rule. And let's just remind ourselves how that works. So if you're using this notation, how does it work? You've got the first times the derivative of the second plus the second times the derivative of the first. If you're going to use the u and v notation, it'll look like this. And of course, you'll remember that the primes are the derivatives. So what they're saying is that we'll now imagine ourselves. Oh, and one more thing I do want to mention here. If you drop the functional notation, then in other words, what I'm saying here is that you have du is u prime dx, and the same thing holds for v. So we have to keep that in mind as we go through what's coming next. Okay. All right. So we're going to take this part and we're going to integrate both sides. So the first thing we notice is that when you integrate a derivative, you're just bringing yourself back to the original function. So here we simply have uv. Now here we've got to make a substitution because you can think of dv dx as v prime. Um, that means that v prime dx equals dv. Okay. Oh, actually, you know what? I just realized what I did wrong. These should have included the dx's. Hold on one second. Let me fix this. There we go. All right, now we're good. So it's already here. So we've got this becomes dv, and this becomes du. Okay, and therefore we have, okay, now, what does this have to do with anything? Well, the rule, integration by parts, is basically set up to solve for the integral of u dv. Okay, so we can rewrite this algebraically, and this is our final result. All right, so this is what we mean by integration by parts. So what you have to do is when you have an integral and you think it might be possible to use integration by parts, what you have to do is figure out what to define as u and what to define as dv. Now, if you do it correctly, you'll end up with a simpler problem. If you do it incorrectly, you'll have a mess. So you'll know to try something different. All right, so let's see what examples they have for us. Uh, Here, oh yeah, so that's what we're after right there. That is now, of course, as always, there's assumptions going on behind the scenes. We're assuming that these functions have continuous derivatives, but assuming that's the case, then we're all set. All right, okay, here we go. X e to the x dx. Classic example of when to use integration by parts because we're multiplying two fairly complicated functions. Now, there's more than one way of doing this typically. Although sometimes there's really only one option. Remember, the whole point of this is to make things simpler. If you choose an approach that's making things messier, well, then you've got to start all over again. So it's x e to the x dx. Now remember, we're trying to sort of fit it into this framework. So why don't we try this? Let's try this to be our dv, and this would be our u. Now, we have to make sure that this is going to work out correctly because, like I said, if you get it backwards, you're almost going to end up, certainly going to end up with a mess on your hands. So here's what we need to do. If u is x, du is dx, then dv is e to the x dx, and then v is e to the x. Now, even though we're using indefinite integrals right here, we're not going to include the c. We'll save that for last. Okay, so in other words, you can leave it out of here. It'll show up later on anyway. So we'll just write down, even though we know that this should have a constant here, but we can save it for the end. Okay, so now what we have to do is take all these definitions and plug them into here and see what we get. And we might discover to our great surprise that it's even simpler. So let's try that. All right, what do we have? So we started out as u is x, dv is e to the x dx. U is x, v is e to the x. And then here we have again e to the x, but du is dx. Well, look, what do you know? This looks pretty straightforward. And there it is. And you notice we saved that C for the end there. Um, when we're defining V here, we don't really need it. So yeah, that's it. That's the answer. Well, that one was pretty straightforward. All right. It's going to get messier, of course, as we go along. What else do we have here? X squared sine x dx. Okay. All right. So again, why don't we try this? And if we got it backwards, we'll notice it right away because we're getting ourselves into a bigger mess. So let's go get the formula again. Actually, before we do that, if we're choosing u as x squared, that means that u is x squared, du is 2x dx, v dv sin x dx. So v is the integral of that. Negative cosine x. And again, we'll save the constant for later. So now we make our substitutions. After a while, you'll have this memorized, of course. So what does that give us? So you have x squared, integral of x squared, sine x dx. Once again, u is x squared. V is negative cosine x. Then we have the integral of negative cosine x, and du is 2x dx. All right, so let's simplify that just a little bit. All right, now you might think we've goofed. We picked the wrong definitions. And well, it turns out, though, that maybe we didn't, because sometimes you have to apply this technique twice. So, in other words, this part is fine. Let's try to reapply integration by parts and see what happens. All right. The second part of this expression, um, at least it's possible that we could reapply this technique and get something a little bit simpler. If not, if it just keeps getting messier, that means we have to go back to the beginning and start all over again. Um, Up here, what happened up here? Hmm. Looks like something got erased here. Oh, there it is. Okay, I don't know what happened there. But anyway, so in other words, way back at the beginning, we started out by choosing u to be x squared and dv to be sine x dx. It's possible that we still got it backwards, that that was not the right choice. But right now, we don't want to jump to any conclusions. So we'll keep what we've got. And what we'll do is we'll try it again, which happens sometimes, to the second term. And if we do get something a little bit simpler, well, then we're fine. Okay. If it's messier, we'll go back to the very beginning and start again. All right. So let's look at this one real carefully. I'm going to start by factoring out or moving out this two here. And then we could try this. So one of these has to be U and one of these has to be dV. Um, let's try this. All right. So we'll have U is X, du is dx, dV is cosine X dx. Oops, sorry, that's cosine X dx. And so when you integrate cosine, you're going to get sine X. And remember, we're saving the constant for later. So let's go get our rule back, in case we haven't memorized it yet. And let's find out what this is equal to. So don't forget the 2 is there, though, that we're keeping that on the outside, but we don't want to lose it. Okay, so we start out with 2 cosine X, X dx. So UV is X times sine X. V is sine X. And du is simply dx. And again, don't forget that too. Okay. And then when you integrate, now, of course, the integral of sine x is the negative cosine x, but we have this other negative here. So we end up with positive cosine x. Now, keep in mind, this is just the second integral. If you remember when we had to reapply, this is what we actually had. So we're going to reunite all these terms basically. So this comes down here. And unless we choose to, oh, and plus now we can add the C at long last. Unless we choose to simplify, we're done. Okay. Yeah, that's it. We're good. Okay. So that was the first time we've seen a case where it may be necessary to reapply um, integration by parts. Now, they give you a really horrendous problem, I mean, it's possible that you have to repeat it more than once too. I mean, if you, it's not an unthinkable. You could have to do this two or three times, but hopefully you won't get anything that messy in WebAssign. But once maybe, but that would be about it. So if you do, as long as you come up with something a little bit simpler, you know you're on the right path. Okay, and that's what happened here. All right. So now what's next? I'm sure they have some very scary examples waiting for us. All right. So here they're trying to help you out by giving you some helpful hints. If you run into anything in this form, like they're trying to save you a little bit of grief by telling you in advance what you're likely to have to do. What should you choose for you, and what should you choose for DV? And so just remember that these are here. Okay. They're doing this from experience. So because otherwise there's a very real chance you'll get it backwards and you'll just make a mess and waste a lot of time. And now they also have this other technique. You don't have to do this, but what they're trying to do is say, well, listen, if you've got one of these cases where you might have to repeat integration by parts multiple times, there's a way of doing it in sort of like a little table. And what they're having you do is this. Once you choose U and DV, they're going to have you repeat both of them multiple times until finally DU brings you to zero. And once you got to that point, what you're going to do is use in your result, as you can see here, you've got x squared, but you're not going to use this one. You're going to use this one down here. That's why the arrow is there. Okay, so if you look at the answer, let me just copy it in here real fast. Um, X squared. All right, I'll see if I can fit this in here somewhere. Just so you can see what's going on. So those two are here. And then now here there's little alternating signs. So you have a negative here, 2x, and this is the integral of this one. Okay. So remember, in this column, you're taking derivatives as you go down. Here, you're taking integrals or antiderivatives. So the product of 2x and this one, 1/16, negative 1/16 sine 4 goes here. And then here's the 2, and here's this result. And you notice stop because this next step brings us to 0. And that's your answer right there. It must have been a nightmare to do this with the integration by parts, and that's probably why they would bring this up now. But they want you to know that this technique exists in case you run into one of these. Okay. So I don't think they have an example of this for us, but instead, oh, maybe this is one. Let's see what this is all about. All right. Um, X to the fourth log X. So we'll start out by trying, well, let's say that U equals, I don't know. Um, let's rearrange it a little. Okay. So let's see what happens. Oh, hold on. All right. So that means, of course, u is log x, du is 1 over x, and then v would be x to the fifth over 5. Okay. Whoops. All right. So let's plug in the numbers. Let's go get that definition back. All right. There we go. All right. So what do we have? So log x times um, x to the fourth dx equals u v minus the integral of v du. Beautiful. Okay. Now we're all set. Okay. Now, by the way, x to the fifth over x, of course, reduces to x to the fourth. And of course, here we use the power rule. And we will need the c. All right. So that's it. I think they want us, though, to simplify it a little. If you look at these options, what do we have here? So you could actually factor out x over to the fifth over 25, which leaves you with 5 log x minus 1 plus c. There it is. And that is what they're looking for in part C. Okay, good. Now, what's coming up is in the next couple of sections, they're going to have more trig integrals for us. Um, yeah, I mean, in calculus, you see trig functions everywhere. So they're going to give us more advanced rules for trig integrals. And so we'll see how that goes. So here now we're done with 8.1 and 8.2. So next time we'll start A3, where we start to look at trig integrals again, at least some more complicated ones, and then I'll see you then. Okay.